how to solve a system of inequations with one objective function at hand, which needs to be optimized. So I'm going to talk about how to solve a system of inequation, or system of inequation, or rather I must say a combination of system of inequations and equations also. So the system can have equations also in it. So we are going to solve that particular system where one objective function will be there, which needs to be optimized. By optimized, I mean we want to maximize the objective function or we want to minimize the objective function, as the case may be. Okay, so I'm going to talk about how to do this. Now, the chapter that I'm actually dealing with right now is linear programming problem, LPP. And the question that I'm going to give you is the following. A very simple question I'm going to give you right now. Number one, we want to minimize a function which is denoted by z. This function is a function of two variables. So I'm giving you the function which is 5x1 minus 2x2, and subject to this function is subject to some constraints or restrictions given by the inequation 2x1 plus 3x2 greater than or equal to 1, and x1, x2 greater than or equal to 0. So this is the problem. And you see in this particular problem, there are two variables, and we can easily apply the graphical method to solve the given system. So we shall apply graphical method. In examination, you don't have to, you need not require to have graph paper to do this kind of problem. These problems can easily be done by drawing axes and curves and straight lines on white sheet itself. So we are going to deal with this particular problem, and since there are two variables only, so it is a two-dimensional problem, and we are going to, first of all, we are going to draw two axes. One axis which will be denoted by the axis x1, and another axis will be denoted by the axis x2, the variable x2. So first of all, let us try to draw it. And we'll denote this horizontal axis by x1 and this vertical axis by x2. And this is my origin. Now in two-dimensional figure, there are actually four quadrants, you know, but here we shall be dealing with only the first quadrant, because in linear programming problem, these variables x1, x2, they are always non-negative. Their least value can be 0, and they can take any value in the first quadrant. You cannot have values lying in the second quadrant, third quadrant, and fourth quadrant. That happens in linear programming problem. Now, this particular function that we need to optimize. Here we need to minimize it, because you know, optimize is the general word which stands for either maximization or minimization. So this problem is a minimization type of problem, and the function which needs to be minimized or optimized rather in general sense is called objective function. This function is called the objective function. Okay. To start with, we don't have to look at the objective function first of all. The role of the objective function will come later. First of all, we'll try to draw the inequation. And you know from our previous class that inequation always represents a kind of region bounded by some straight line. Here the power of the variable x1 and the power of the variable x2 is 1. So this inequation is a non-linear inequation. First of all, we will consider the corresponding straight line form of this particular inequation. This given straight line is this: 2x1 plus 3x2 equals to 1. We always can draw the straight line because equality sign is there. And you know that we have to draw it by considering the straight line in its intercept form. So we are going to divide the equation in such a manner so that we get a straight line form of a straight line equation of the form x by a plus y by b is equal to 1. This type of form, this type of intercept form we actually require. Okay. But you see, on the right hand side of this intercept form, 1 is there. And here in this equation, 1 is already present. So what we need to do, we have to bring it into something like x1 by something and x2 by something. So we need to write it as x1 by something so that it takes the form of x by a, and we need to write it as x2 by something so that it takes the form y by b. And we can easily do it by dividing the thing by half, because x1 by half is same as 2x1 and x2 by 1/3 is same as 3x2. Now you see, you just compare this equation of general equation which is written in intercept form with this given equation, which is x by half plus x1 by half plus x2 by 1/3. And you know that this quantity half is the intercept at the intercept on the x1 axis, and this quantity is the intercept on the y axis. That means x2 axis. So we shall take a point. So for example, arbitrarily, if I consider this to be, say, we can do it by visual inspection. So if this is this point we can consider as 1. So half will be some midpoint of that. So this is my point half, which has the coordinate half comma 0. And we can name this point by A. Okay, so you can always do this by visual inspection. 1/3 is approximately equal to 0.333. It's a recurring decimal. Half is 0.5. So if I consider this point to be 1, and this is the midpoint, say half, on the x2 axis, so somewhere here, arbitrarily, this particular point will lie. So we shall name this point by B, and its coordinate will be 0, 1/3. Once we get these points, we'll draw the straight line. We'll join these 2 points by straight lines. So let us join it. Okay. So, and since there is only one restriction, that means only one constraint is there. So only one straight line will be there. Okay. Now, if you can recall that, as I told you in my last class, that to mark the region, we need to consider this point 0, 0, its coordinate is 0, 0. We have to mark this origin, and we have to substitute x1 equal to 0 and x2 equal to 0 respectively on the left hand side of this inequation first of all. So what we'll do, I'm writing here, step 1 was draw the straight line. Step 2 is substitute 0, 0 in the constraint. Constraint means the inequation I'm talking about. Constraint. And you know that if 0, 0 satisfies the inequation, the region will be on that side which contains 0, 0. But if I substitute 0, 0 in this inequation, 2x1 plus 3x2 greater than or equal to 1, you see that we'll get 0 greater than or equal to 1, which is absurd. And therefore, it is not satisfying the given inequation. And therefore, the region will be that side which doesn't contain 0, 0. So let us mark the region. So this entire half, let me do it by some other color. This entire portion, the upper side of this straight line, the entire, everything bounded by this straight line. This region cannot cross this straight line, it cannot come below. And nothing will come on the second quadrant, because otherwise x1 and x2 will become negative respectively. Nothing can fall in the fourth quadrant, nothing can fall in the third quadrant. Everything will be on that side. Everything bounded by the straight line. So this portion, this entire portion will be the respective region of the given problem. Okay, so this is my step number 2. So we have marked the region. And since there is only one constraint, so there is only one line. Let us denote this line by this straight line that I have drawn. Let us denote this by L1. Okay, if there are more than one lines, we will denote respectively them by line 1, line 2, and so on. So this is my line 1. This corresponds to my line 1. Okay. Now you see that this particular region, remember this region is actually what? This region is actually not bounded from the upper side. I mean, it is not bounded from this side. It is unbounded actually. Okay, no boundary on the above, but it is bounded from the lower end. Okay, so this is the boundary. The coordinate of this type of region that we have obtained, this type of region which is unbounded on one side and bounded on the other side, this type of region is actually called mathematically it is called convex hull. And here we'll call this region as the feasible region of the given problem. So this region is called the feasible region of the given problem. Okay. What we need to do next is step number 3 is to find the coordinates of the corner points of the boundary. Corner points of the boundaries that bound the feasible region. Feasible region. Now you see that since the region is not bounded from the upper end, it is only bounded from the lower end, its coordinates are already marked. Okay, and this coordinate, it has got two coordinates, two corner points. One corner point is this one, and another corner point is this one. So we'll write, with respect to step number 3, we shall write the corner point, A has got the coordinate 0.5, 0. The corner point B has got the coordinate. The corner point B has got the coordinate 0, 1/3. Okay. So the corner points of the boundary is marked. Now what we do is, in step number 4 is the following. In step number 4, we will substitute these coordinates of the corner points these coordinates of the corner points in the objective function. Okay. Now you see what happens. So if I substitute the first corner point, the objective function is what? Z. It is denoted by Z. We are going to substitute x1 equal to 1/2 and x2 equal to 0 in Z. And that gives you 5 into 1/2 minus 2 into 0, which is 5/2. Okay. This is the point number 1. Point number 2 is that another corner point is still remaining, which is having the coordinate 0, 1/3. We are going to substitute that corner point in the objective function also. So that corner point has got x1 equal to 0 and x2 equal to 1/3. If I substitute, we get 5 into 0 minus 2 into 1/3. So we get minus 2/3. And no more corner points are there. Okay, no more corner points are there. All the corner points have been substituted. Okay, so can I go to the next page?
Yes, sir.
Yeah, okay. So all the corner points are I have substituted over here in the objective function. Now there is a theorem in the linear programming problem. The theorem says that if you want to find the optimized value of the objective function, that is the maximized value of the objective function or the minimized value of the objective function, we don't have to substitute every point on the objective function. You see, actually this region that I have marked by purple color, this region lying on the two-dimensional plane, here, everywhere, thousands, millions, trillions of points, infinitely many points are there actually. Okay, many points. I'm marking them by dot. Theorem says that we don't have to mark, and each of these points that I'm marking over here, each of these points will have some sort of coordinates. Okay. It is not required that you need to substitute all the coordinates of all these possible points in the objective function. The theorem says that if you want to find the optimized value of the objective function, then just take the corner points of the straight lines which bound the feasible region, and you substitute those coordinates of the corner points only in the objective function, and try to find the maximized value and the minimized value. Okay, so keeping this in mind, what we need to do is that our job is done. We don't have to do anything at all because only 2 corner points are there, as we can see. So, and here you see that this particular problem is actually a minimization type of problem. It is a minimization type of problem. So you see that after substituting these coordinates of the corner points here and here, we got 2 values. One is 5/2 and another is -2/3. And obviously this particular value, that is the second one, -2/3, is the minimum of the 2 values. Okay, so the minimized value of z, the minimized value of z is equal to -2/3, and the minimized value of the variable x1, the optimum value of the x1 is 0, and the optimized value of x2 is 1/3. Because for these values, because of these values, we have got -2/3. So our solution is that the objective function has been minimized well, and the minimum value is -2/3, and the corresponding values for the variables x1 and x2 are respectively 0 and 1/3. Okay, so we get this solution for the given linear programming problem. Now, in the next page, what I'm going to do is the following. I'm going to keep this problem same. I will change one particular portion of that. Okay, so let's just concentrate. Yes, you want to say something?
Sir, can you please go back to the previous page just for a second? I'll take a screenshot.
Yeah. All of you, please take the screenshot. You don't write anything, because if you try to write things, then it will just kill time. So you just understand and take the screenshot, and you don't have to worry. Okay. Now, in the next problem, I could have selected another problem from the book, but I'm concentrating on the same problem that I've done over here. And let's see what happens. In this particular problem, what I'm going to do is the following. The objective function z is 5x1 minus 2x2. This remains same. It is subject to the constraints. It is subject to the constraints 2x1 plus 3x2 greater than or equal to 1. x1 comma x2 greater than or equal to 0. But here I am writing maximize z. So my problem is now changed problem. Previously, our job was to minimize the objective function. Now I'm going to maximize this particular objective function. I'm not going to draw the figure once again, because this is the same figure. Oh, so it will be just a mere repetition of the same thing. So for this particular problem number 2, in question number 2, you have to draw the same figure. So I'm writing here for your sake, draw the previous figure. Draw the previous figure as it is. Put all the corner points, put all the coordinates, mark the region, everything will remain same. Okay, no problem. Same graph will be obtained. So I'm not drawing it, I'm not repeating this by drawing the same graph, but analysis will be different. The analysis will be, you see, if I look at the graph now, you will find that we want to maximize this objective function. Now, this is the lower end. This is the lower end. This particular region is the lower end, which bounds the feasible region of the problem. Obviously, if we want to say something, anybody? If we take any point, be it corner point or anything, if you can take any point lying on this particular straight line, if you choose its coordinate, it is always going to give values which will be lesser than those values which will be obtained by substituting the coordinates of these dotted points. As much as you go further from the straight line above, in the above direction, in this direction, as much as you increase the value of x1 and x2, your objective function z is going to have max and max and max values. If I take a point, if I take the point this, if I take the point this over here, I will get some value for z. Now someone takes points from here, he will get some value which will be greater than the previous one. If someone takes the point here, he will get some values which he will get some value for the objective function which will be greater from the previous two values, and so on. And we can always take points from here and there because there is no boundary on the upper end. It is unbounded, it is open. Okay, so the analysis is that as much as you increase the values of x1 and x2, your objective function will keep on increasing. And therefore, from the previous figure, from the same analysis, we can write that analysis is the following.
Which one keeps on increasing?
x1, the value of x1 and value of x2. If I take this point, okay, if I take this point, obviously this point will have some coordinate. This point will have some coordinate. Okay, and if you can mark the coordinate, if you substitute this coordinate in the objective function, you will get some value of z. Say this value is z1. If someone takes this point and he marks the coordinate, this point also lies on the objective function. So if he substitute this coordinate on this particular function, he will get a value which will be greater than the value obtained by putting this point. This point will give you some larger value. If someone takes a point here, it will give some other value which is larger than the previous two, and so on. So if you keep on increasing the value of x1 and x2, the value of the objective function will keep on increasing. Why it is happening? Because there is no boundary on the upper end. It is open-ended system. So the analysis is, since the feasible region is not bounded from above, so the value of z will keep on increasing as long as we increase the value of x1 and x2. And so this system, this question number 2, has unbounded solution. Unbounded solution. So you see, if I compare question number 1 and question number 2, a minor change in the problem gives a huge change in the solution. Previously, the problem was of minimization type. Now this problem is of maximization type. Previously, we got some value which is fixed. Now we are getting some values which is not fixed. And this sort of problem is called the unbounded. This sort of problem is said to have unbounded solution because of this type of figure. Now, don't think that if this problem comes in the examination, you have to write this single sentence only. No, you have to draw all of the things that we did earlier, in the previous case. I mean, you have to draw the graph, you have to mark the region, you have to put the coordinate. So this is left for you. Since the same thing is coming, so I didn't repeat it, drawing once again. So I wrote only the solution of the given problem. Understood? Have you understood the two problem? Any doubt?
No, sir.
Okay. Now I am going to take a third problem where I am taking the same objective function 5x1 minus 2x2. Okay. Subject to 2x1 plus 3x2. Now I'm changing something over here. I'm writing it as 2x1 plus 3x2 less than or equal to 1. And suppose this problem is a bolo. Yes.
Sir, second question answer unbounded
Unbounded
solution.
solution. This is the answer. Unbounded solution.
আর গ্রাফে ওখানে মার্ক করে দিতে হবে পয়েন্টটা যে
No,
unbounded যে পয়েন্ট আছে
unbounded points cannot be marked because it is unbounded. If someone marks these points, some other will say that no, this is the point. Some other will say no, this is the point. This is the point. How many points will you mark? These 2 points
না
that
আমি বলছি এরিয়াটা কি এরিয়াটা
the region has to be marked. You will draw the axis, x1, you will draw the axis x2, you will draw this straight line in green color, you will put the point B, you will put the point A, you will mark their coordinates, and you will denote the region by the purple color. You will explain why it is this purple color is denoting the region, why it is so. You will explain it. After that, you will write this analysis. Understood? Now I am changing the same problem a little bit further. Let us consider the minimization type problem as it is. And constraint is now changed. Instead of taking the greater than equal to 1, we are taking less than or equal to 1. And other are not changing. X1, x2 greater than or equal to 0. And we are going to draw this curve because it is something different. So first of all, we will draw the axis as before. So this is your x1 axis, this is your x2 axis, and you will mark these two, and you will put the point here. You already know what is the straight line, so I'm writing here. I don't have to recalculate. So this is the point which is 0.5, 0, and this is the point. If this is the point 1. Then this point is B, which is 0.1/3. And only one straight line will be there because the number of straight lines have not been changed. It is same. What changes is that the inequality. The inequality is now changing. So after drawing this curve, after drawing this straight line, what you need to do is that you will write after substituting 0, 0 in 2x1 plus 3x2 less than or equal to 1, we see that it satisfies the point, the inequality. So the region will be that side which contains 0, 0. So in this particular case, the region will be this portion. This is the region. And such a region which is bounded from all sides. You see, it is bounded from the lower end, it is bounded from the upper end. It is a kind of closed region. It is obviously a feasible region. It is obviously a feasible region of the problem. And such type of figure is called convex polyhedron. A definition, a mathematical definition of convex polyhedron, I have not yet discussed, but I am, with respect to the problem, I am trying to understand the difference between the two. Previously, that was unbounded from the upper end, so that was convex hull. Now it is unbounded from all the ends, so it is convex polyhedron. So this is in very rough sense. It is not the actual mathematical definition. Actual mathematical definition I will give to you later on. So this is the convex pole.
বলছি যে রিজিয়নটা মার্ক রিজিয়নটা যে 0 থেকে বড় হচ্ছে ওটা কি করে আমি বুঝবো স্যার মানে ক্যালকুলেট করে দেখে
this is the thing.
হ্যাঁ
Now zero marked region is I explained in the previous class that to mark the region
I have to put 0 in the equation
in equation and if the 0 satisfies the inequation, the region will be that side which contains the 0. So this side is containing the 0, but in the previous figure 0 was not satisfying the inequation, because if I put 0 over here we get 0 greater than or equal to 1. It is absurd. So the region will be that side which doesn't contain 0. So we draw the opposite end. So now it is a closed region, and this how many corner points are there here? Now there are
in
3.
previous there was geo too. 2 geos were there in previous one.
What was there?
I'm telling that so y side is not drawn towards the geo angle
Because it is not
So why it
satisfying
is,
the inequation. It is not satisfying the inequation. If I put 0 in these 2 points, what we get on the left hand side? 0.
Yes, sir.
On the right hand side, what we get? 1. So 0 is greater than or equal to 1. It is absurd. So this inequation is not being satisfied by the point 0. So therefore we are not drawing this portion. So we are drawing the opposite, which doesn't contain 0. Here it is not happening.
Okay, sir.
Here it is if you substitute 0, it is satisfying because 0 is less than 1. And therefore we are drawing the portion of the region which contains 0. So there are 3 corner points now. 3 corner points. Previously there were, in the first problem, there were 2 corner points only. So there are now 3 corner points. One corner point is A, 0.5, another corner point is B, 0.1/3, another corner point is 0 itself, origin. Quickly take the screenshot because I'm going to lose this session. Less than 1 minute is remaining. We'll continue in the next class. I mean next session.
স্যার এইটার পরে কি লিখেছেন আমি ঠিক বুঝতে পারছি না স্যাটিসফাইজ দা তারপরে
Satisfy the inequality. It satisfies the inequality. I'm going to continue in the next session. Don't ask now. Ask me in the next session, because it is going to